Today is the fourth and the last colloquium for the fall semester of 2005. This California Water Colloquium has been going on for about 5 years now, and we are delighted that it has taken root, if you will. And we have had some wonderful speakers that have broadened our horizons about water, both the scientific aspect of it, the political and human aspect of it, as well as the aesthetics of water. Water is such a magnificent, mysterious substance, which provides inspiration for all of us. Today we have a speaker who is going to introduce us to a new topic that we haven't heard much about in this seminar series, about climate. We have talked about water in rivers and streams and below the ground and all that kind of stuff. But what drives water on the earth is the climate. And climate is so crucial that, but fortunately or unfortunately, we have to wait 5 years before we started hearing about climate. Last month we heard about, for the first time, about glaciers. This month we are going to hear about climate. The speaker is Dr. Norm Miller, who is a research scientist in the Earth Sciences Division of the Lawrence Berkeley National Laboratory. He is a hydrometeorologist. He concurrently holds a position of professor with adjunct stature in the University of Arizona at Tucson. At LBL, he leads the group devoted to atmospheric and ocean sciences. And he has done substantial amount of serious work on climate change. And he has been recognized by being invited to the intergovernmental panel on climate change, which is perhaps the most authoritative body about any information that we can get on climate change. Climate change is such a substance that everybody talks about it. But if you want some reasonably authentic information, it comes from the IPCC, of which he is a contributing member. He has done a lot of work, computational and otherwise, on the climate. And today he's going to talk to us about climate change and its impact on California, especially about California's infrastructure.
I think I got this mic here. Thank you, Nari. So I put a little hook out in this title, thinking it might get some new people. And what I'll do is primarily go through a little bit of a historical background on what we know about California's climate, just briefly, and then I'll go through a brief introduction to the outcomes of some of the climate simulations in some of our earlier studies, myself and many others, as well as some new people, and then how it's impacting California water systems and some other sectors. And then I'll get back to this earlier question about infrastructure and then lead it into a discussion. So if we talk about the climate trends and what we've seen, the real compelling question that people are asking right now is really whether or not the water cycle, the global water cycle, is accelerating. And that's really what we focus on internationally through a number of different observing organizations, including the Global Earth Observing System of Systems. And if you go back about 800 years or more, You can look at indices as to whether or not we were in wet or dry regimes by using isotopes. This is an example where Lynn Ingram from Berkeley looked at some of the sediments, and she was able to use a way to determine whether or not the salinity was high or low. And it just tells you if the salinity is high, you have a lack of fresh water flowing out of the Sierras into the delta and bay, making it seem like a dry regime. And if the salinity is low, it's quite the opposite. So what we see here is right now we're in a little bit above average wet regime historically. But what's really important under natural climate variability are these very long dry periods back in the 1500s. So California is living in this sort of mythological wet regime where we brought all this agriculture and water transfer in. And we don't really know whether or not under natural climate variability it will last. So that's one of the first things I like to just put out there for you to think about. And getting to more contemporary things, we've been observing the climate, observing it from the ground, observing it from satellites. And a real good picture here I got from someone is the summer from 1985 compared to the summer in 2002. And this is a real important thing because Lonnie Thompson from Ohio, who's been measuring ice for years and years and years, and you heard about it last time, he's been saying by 2025 it'll be gone through all the alpine regions in the world, pretty much. A lot of the glaciers are going to be gone. So this is sort of a takeoff from the last one. Just to hear a little bit more about what we've observed, there's been an indication of all the rivers that we've seen in the Sierra Nevada having their flows, their snowmelt runoff flows occurring earlier and earlier. Around 1910, you can see here the percentage of the annual flow in springtime was on the order of 45, 50%, but then it starts decreasing. And you can see this for the American River. And this just tells us that there's a signal out there, sort of like the canary in the mine type of signal when you see these types of measurements being seen in many of the alpine regions around the world even. So more recently, I guess this was in, well, 1999, Michael Mann and a number of others came out with this first hockey stick type of feature that goes back 1,000 years. And what we see here in the observed record right in here is that we've been dramatically increasing the global near surface air temperature. And as you go back in time, you can see that it's really not gotten this warm since the last ice age, at least. So that's very important. And in fact, 2 weeks ago in Nature, they verified this even further back in time, looking at some of the Antarctic ice cores. And that's sort of a new paper. Whoop. OK. That shouldn't be doing that. No. All right. Now, in addition to some of these types of events, focusing on whether or not the hydrologic cycle is really accelerating or not, the measurements since the last 100 years really have shown that precipitation, the extreme precipitation, the 10% of precipitation that is the most intense, has actually been going up from about 36, 37% in the beginning of the century of 1910 thereabouts to about the end of the century. And heat waves have been going up. So you're starting to see all these extremes popping out. And when we see these extremes, you start to ask questions about how often they're going to occur in the future and what's it going to do to California's systems, electrical systems, the Western US electric grid, for instance, and water, because water is kind of vital for everything. And you could just see this last summer, above average heat extremes. All records were set in this region. And if you look at the forecast going out till next year, it's going to be the same. So that's the trend. That's the trend we're seeing. And as we look at more and more of these trends, you see there's a very good relationship between the atmospheric greenhouse gas concentrations and the near surface air temperature globally. And this has been around since 1955, these types of measurements here. And the ice core data has taken it back even further. So the IPCC was formed in the mid-'80s, and I've been participating in that since about 1993. The last three reports, the fourth one's coming out in about a year and a half. And a very careful set of likelihoods were put together in the 1995 second assessment report. And what you see here are 99% certain likelihoods with 3 stars. 3 stars being the sea surface temperature and the retreat of these glaciers that we're seeing everywhere going away. The 2 stars is between 90 and 99%. And what you're seeing there are the extent of the snow decreasing and the temperature that's been observed in general over the last 100 years that's been going up. So these are some of the main indicators that people are using to look at the global temperature impacts. And there was sort of a grassroots effort. I had done some early work in about 1995 on looking at projected stream flow. And then we worked with the Union of Concerned Scientists and came out with this report in '99, and it sort of built some momentum that led to a number of new studies. So this is the first part I'm going to talk about that was sponsored by the state. And in this study, we looked at one greenhouse gas emission future, and I'll talk about what that really means in a second. We looked at 2 global climate models forced by one emission going out 100 years. And in this particular set of studies, because the time was, we had to do it in 6 months, we used statistical downscaling approach as opposed to a dynamic. And to pull in a lot of the government, what I did is I worked with the National Weather Service River Forecasting Center. And I'll just really highlight what this means. The Intergovernmental Panel for Climate Change has a group that has put together scenarios, a special report for emission scenarios, and this is updated every so often. It takes into account behavioral, cultural, and emerging countries and how greenhouse gas emissions would evolve into the future. And up until recently, all the studies used this 1992 emission scenario. It's called the IS Interpanel for Government Scenarios, 92A, this black line. And essentially it goes from about 7 gigatons of carbon, which was the 1990 level, up to about over 20 gigatons. So it's almost a tripling. And when you look at the climate models forced by that one emission scenarios, you get this whole spread going out into the future. And in our case, we used the, this blue one here. It's called the Hadley Climate Model version 2. It's this blue line here that gets up to about 5.5 degrees globally by the end of the century. And we use the US parallel climate model shown down here. And when we talk about future climate sensitivities, that's really the difference between the temperature out here and this historical period. So when we say this Hadley model has a low temperature sensitivity, you can see that it's a little cooler compared to the little warmer one. So this has got a medium sensitivity, it's got a low sensitivity. I'll talk more about what that shows. Now, this particular study was used for a lot of the state studies when we finished it. And what we did here is we looked at temperature changes, precipitation, stream flow, and then how those affected the snow and the snowmelt, the runoff, and floods, future floods. And I'm just going to breeze through a little of this quickly and not focus too much on all this. But what we did is we took 2 climate models, one that is compared to all the models going out in the future, it's relatively warm and wet. That's the one right here. One that's relatively cool and dry. It still gets warm, but it's a low temperature sensitivity model. And we forced it, it was forced rather, with this emission, and then we looked at all these outcomes. And we used a well-recognized hydrologic model that the state runs. And we used their calibrations, and there's some tricks associated with non-stationarity that we were able to navigate around by doing these so-called perturbation studies. And this is the model that we used. It's called the Sacramento Soil Moisture Accounting and Snow Model. And what we did is we took the global climate model data, which is very coarse in resolution. It's about 120 kilometers on one of these grid boxes around the world. So this represents a single grid box, if you will. And we downscaled it to these 10-kilometer grid boxes so that we can get down to these watersheds for the Sierra Nevada. And then we were able to get temperature and precipitation at this finer scale, and then look at how the snow line here changes, how the snow melt itself is changing, what the runoff is doing, as it's forced by two variables, temperature and precipitation for this watershed. Those are called mean area temperature, mean area precipitation. And I chose a set of watersheds early on to try to capture the pulse of the system. And it turns out it's this set that everybody uses now in California. And I picked these intentionally because this one up here is coastal, it's rain dominated. The Sacramento and the Feather flow into the Sacramento itself, as does the North Fork. These are all different sizes and elevations. And these are two very high elevation southern ones. And so this really can give us, with a sparse piece of information, how the whole system works without calculating everything. And you sort of have to play that game. Otherwise, you have an over-parameterized problem. Now, what I show here are a set of figures, and I'm going to show a bunch of these. So I'm going to explain them really carefully so that it's really easy. Warm and wet is the type of climate model that I referred to earlier. That's the one that represents the Hadley model. Cool and dry is the US model. And when we calculate these downscaled values, we get different temperatures for each month. Here you see a year, October, November through August, September. This is called the water year. And each of these are a basin, according to what I showed you earlier, the Sacramento, the American, the Merced. And what you see here in blue, in green at the bottom here rather, if you're not colorblind, are the historical mean monthly temperatures for each of these basins. And then as you go to the green, you're going out to, well, the blue with circles is 2010 to 2039. And then as you go out further in green, it's 2050 to 2079. And then finally, at the end of the century, which is probably the one to focus most on right now, is red. So that temperature looks really well behaved, and there's a lot of reasons for that. It's something that climate models can do a fairly good job on. But when we start to look at precipitation, it gets into all this nonlinearity due to the way cloud processes work and are not as predictable. So what we're seeing here for the precipitation is big differences between the two different models, the warm-wet case for these same sets of watersheds, the American in the middle, the Sacramento, and the Merced. I'm just showing three here just to give a snapshot of the whole system. And then over here. And as you go out in time, you see how it gets really, really large amount of precipitation towards January and February over the American, Sacramento, and so forth for the warm-wet model, which you would expect. It's warm and wet. But in the Sacramento, I mean, in the cool-dry version, it doesn't do quite the same. In fact, you see all these shifts in the timing of the maximum amount of precipitation. And so it's these two variables that go into the river model that I just mentioned, the Sacramento model. And when you put them in, you get the mean stream flow. So in these two cases, they're very, very different. And the reasons that they're different is this one has a huge amount of moisture going into the system. It's warm. And what's most important is you see this big peak here. And this big peak is an indicator of a shift between the rain and snow ratio. Typically, snow is stored until spring, late spring, early summer, depending on the elevation. And then it's made available as it melts for reservoir irrigation and so forth, for hydropower. Here, it's much lower. And the timing doesn't seem to change as much. We're here, for example, in the Merced River, which is very high elevation. The peak flow is around the same time, but you get two peaks. And the reason you get two peaks, I'll explain later. in addition to looking at these two climate models, we put together a set of scenarios that we specified just to create a matrix of potential outcomes to understand how everything might behave. And so if you look at this panel in the middle, again, this temperature change and precipitation change for historical are the dark blue lines. It's the same as the figure before, but now the temperature is going up to 5 degrees warmer in each case for this whole system, and the precipitation here gets 30% greater and 30% less. And what you see are these dramatic shifts in the timing of the stream flow for the entire California system. So this gives you a whole sense of how precipitation going across horizontally and temperature going across vertically change for the entire system and for each month. And just to get an understanding of how these sets of climate models, this is the warm, wet, cool, dry, and then the set of very extreme scenarios, a very, very warm case that's wet, and then a dry case where these green circles here are almost reminiscent of what we would call a long-term drought. And what we've done in some of the research right now with the Department of Water Resources is begun a series of 30-year drought simulations to see how California will respond to all this. So the real question is, what's the mechanism behind all this? And if you look at the amount of snow water equivalent is the amount of snow up in the mountains for each month. And if you imagine there's an amount of snow each month, historically, that's this black line. And as we go into the future, the ratio of the future amount to the amount historically represented by these lines going down. And again, blue is early century, green is mid-century, and red is end of century for each of these watersheds, the Sacramento River Basin, the American River Basin, and the Merced here. And this is the warm, wet climate model going out 100 years, where this is the cool, dry. And the most important finding is that regardless of the climate model, that is a warm, wet relative future or a cool, dry, warming future, relatively cool, you still see these large decreases in the amount of snow. And this is really an important finding that tells us it doesn't matter about the uncertainty in these climate models, because if you look at these two end members, a relative warm, wet, a relative cool, dry, we're still going to lose an awful lot of snow. Now this one's a little bit different because it sits very, very high. You can see here that its elevation is over 2,500 meters, where this one is at 1,700 and this one's at 1,700. So it plays a much different kind of role because it sits above what is called the sensitive zone, where the snow line is creeping up. And I take this one step further. When we ask, okay, so now we know that the amount of snow is decreasing, then the question becomes, when is it melting? And if you look at the ratios of the historical snow melt, that's this black line again. Everything is similar to the previous figure. The ratio then tells us in the future we get these huge melts in the winter. And these huge melts here and here and here and here and here are indications that the stored snow in the wintertime is no longer there. It's moving through the system fast, and it may very well be in the form of high river flow floods. And again, I just show this for this set of cases where this is sort of the middle case. And we go into a case where the precipitation decreases, precipitation increases, and as you go up, it gets warmer and cooler. Basically what you're seeing here is a general trend for these big spring, rather winter, December, January, February periods where it's all melting. It's moving through the system. And this is consistent with some of the other studies that have taken place since this work, which was in about 2001. And I guess it was published in 2002, 3. And to see how this really responds, again, this color code is all the same. Blue is historical, green is early century, red is mid, and blue, light, or red is end of century, I'm sorry. It just shows us that the middle halfway cumulative amount of water going through the system is occurring earlier for these cases. Here it's a little diffuse because this is a very dry scenario. It's drying down. And so when we ask the question about can it break our infrastructure, what's going to happen, they're going to have to release water for it to get through the system. And to understand high flow conditions, I looked at what would be called a 30-year high flow and looked at when they occur. For example, in the American, the high flow for 30 years is called the exceedance. And the 99% exceedance is right here, which tells us that the high flow is somewhere around 1,500 cubic meters per second over the last, since 1960. That's the highest flow. In the future, it could be as high as about 3,500. So that would be a substantial flood. In Sacramento, we have the same case. Even in these dry scenarios, they pop up. And so this leads us to believe that if temperature continues to increase and snow melts earlier, we're going to see water moving through the system faster, and there'll be conditions where it can have very high flow. I'll skip some of this and just end this first part so I can move into the more interesting stuff. So far, what have I told you? I've told you that the temperature and the precipitation are governing the watershed response, and that a lot of things associated with the actual topography, the elevation, how air systems are directed control it as well. But most importantly, the sensitivity of the elevation to where the snow line moves is going to govern when we see this kind of melt. And there's a shift in the magnitudes. And in this first study, we see that the magnitudes shift by mid-century, and but it's not really significant until the end. And at this April 1st is a time period when people measure the amount of water available for different users, agriculture, and the amount that's going to be flowing through the system for fresh ecosystems to be sustained. That's going to be reduced by about 50%. That's what this study outcome showed. And the wintertime melt increases quite a bit, and this is what leads to floods, but the summertime amount decreases, which may lead to short-term deficits for the need for water. And finally, the last set of figures just say there's a really good chance of floods. So I'm going to get into this second part so that I can get through what I really want to get to. Now, we started another study that was funded by the California Energy Commission, and this time we did something new that really starts to get into behavior, because we start to look at different types of emissions. And I'll explain what that means in a minute. And this time it was a whole group of people. In fact, we got into the proceedings of the National Academy with this work, and we begin to ask questions here, more importantly, about behavior. What are the consequences of different emission pathways? You know, if we go the Cheney route being what I call 6 times the 1990 level, where it's a fossil-intensive future and SUVs are everywhere, or if we go into more of a local energy, soft energy type of future, we may see a doubling. And this is the big question. What is our society, our global society, really going to do? And when we did this, we again took 2 models, but we this time took a more recent version that has a slightly better response, if you will. And we have 4 outcomes, which helps us to bracket, instead of just by the sensitivity of the climate models, but by the climate models and then the emissions. So this really helped us. And in doing that, by choosing it with different emissions, one of the grandfathers of climate modeling from NCAR in Boulder, Colorado said, this is one of the first papers to really approach it this way, and that it's going to be repeated by many others around the world. So that made us feel good. And last time I showed this, I said we used this scenario, the IS92A. So this time around, we use the A1FI. This is the Cheney future, or maybe this one is. It's hard to say. And then the B1. So this really gives us a much bigger range of emissions. And again, just to jog your memory, this is the low sensitivity model, but this time we use the Hadesium-3 here in brown, which is a little warmer. Globally, it gets up to, by the end of the century, that is, it gets up to about 5 degrees globally. But in California, it gets up to 8 degrees Celsius. Just thought I'd let you know. So in the wintertime, we see these changes in temperature going out from 1990 to the end of the century. Our earlier studies showed the range lied around here, but now it moves up. Again, this here is the warmest case. This here is the not so warm case. So you can see that range. But what really was striking is that summertime temperature. This is what we find for all of California during June, July, and August is over almost 10 degrees during that time period. And when we, again, statistically downscale this thing, you can see here the different cases. I believe this is winter, this is summer. And the different model, the low sensitivity case, the high sensitivity case, and then in the summertime you see this horrendously warm figure saying that it's going to be hot. So hot that, you know, we need to do some more work to figure out what it really means. And we use this to a lot of legislatures, this picture. In fact, we went around doing a lot of things. In fact, the group that was on that paper helped to put through the Pavley bill by showing these pictures. And just to get an idea of what's going on, you can see some pretty hot temperatures toward the end with the worst case scenario. 18 degrees Fahrenheit, or at the most extreme for a heat case, is on the order of about 10 degrees Celsius there. So I, in particular, started asking questions about heat, because heat, to me, seemed like a real kind of standout problem. And you find that when we look at these 4 potential outcomes that I've been talking about, the Hadley model under the very high fossil-intensive future, an information type future, and then the low temperature sensitivity model in that fossil-intensive future, and then under the information future, you see these heat waves start much earlier than they do now. Onset of heat waves can happen almost 2 months earlier than we do now. And of course, that's going to have an impact on a number of things. They're going to have an impact on utilities. They're going to have an impact on human health. So again, the temperature gets all the way up to about 10 degrees. That's the important feature here. This is the range of increase. And what I did is I took a look at a number of cities around California and now globally, and started to look at how often it gets above a certain temperature. The National Weather Service uses 90 degrees Fahrenheit as one of their thresholds. There are a number of ways to look at this, including the 90 percentile. And if you just look at how often it gets above 90 degrees in the LA basin, I'll explain these lines here. This is Los Angeles basin, and these are the temperatures, and this is how often something happens. When you talk about exceedance probability, it means how often it happens, and 50% is it happens half the time. 90% means that everything above it happens 10% of the time. And when you look at the 32 or 90 degrees Fahrenheit, you see that it happens about 5% of the time historically. Black is historical. Red is at the end of the century, so you can see how these go out. And at the end of the century, the 2 models, the solid one is the low temperature sensitivity, and the dashed one is the high. It could happen to almost 30% of the time. The whole summer could be a heat wave. So what does that mean? When the worst case scenario tells us that 95 days can be above 90 degrees. Well, you know, heat kills more people than any other natural disaster. In fact, it kills it more pretty much than all the others combined. Even with the tsunami up here in the future, this still sits at the top. You know, maybe it's offset right now, but that's a short-term change. So this is part of a new report, actually, and I'll just show this figure, and we need to be careful about some of these figures. What does heat do to people? Well, you can see in LA, it's going to go from our current level to about 2,000 in the early part of the century, or this is the early historical part, and by the low emission end of the century, it's going to get up to about 6,000, and in the worst case, it's going to get up to as high as about 11 or 12,000. And there's a lot of factors that come into play, adaptation and how people respond to heat. And I'll just pause for a minute and say I completed a study on energy demand as well, and we're about to submit that to Science, so I'm not showing it. But the finding that we have is that there's going to be a huge load on the system, and it's not clear as to whether or not there'll be enough capacity. And if we just talk a little bit about precipitation, that's still a very big unknown. And in these sets of studies, it just kind of floats around, and you see these strange-looking increases. They're really not well understood, and they have to do with a combination of modes of natural variability and a number of other mechanisms. But there seems to be a trend in these studies here for either to stay about the same or slightly decrease. So we don't place a lot of we don't put a lot on the precipitation itself. We do put a lot on the temperature and the change in the ratio of snow to rain. There's going to be an increase in rain compared to snow in the mountains. And when we look at precipitation in the wintertime, you can see, again, these different models showing this is the very warm scenario. You get this is a decrease in moisture. It's drying out. That's why we saw a decrease in all these cases except for one. This case shows that in the wintertime, and there's a long story behind what we see here, but basically it's just a slight increase. And when we look at the downscaled signal on the precipitation, you can see in the wintertime where you get the majority of precipitation for California, all the cases decrease except for that one that I just showed you. And now with these two separate scenarios that I mentioned, we get a slightly different change in the amount of snow compared to what I said in the first part. At the end of the century, we thought it was going to be about a reduction to about 50%. But now, at the end of the century, we're seeing how it's dropping off in each of these panels here. And under the worst case scenario, which is this fossil-intensive future with the Hadley model here, hope you can read that, we're getting to about a 80% reduction, on the order of about 10 to 20% remaining of our snowpack. And our snowpack represents on the order of 60% of our fresh water, and our groundwater, makes up the rest. And that's why we asked the question about how does the surface, subsurface system respond, and will we come to a different equilibrium in the future? This is pretty important, because if we don't have enough fresh water, we won't sustain ourselves. So just a couple of other things. Everybody probably knows about the sea level rise and thermal expansion as the upper water layers warm. They expand based on the equation of state. So people are talking about a meter increase in the sea level. And this is just those four outcomes again, where it could range between somewhere around 200 millimeters to 500 here. People are talking much higher, but a figure the Army Corps of Engineers came out with, surprisingly, shows here that what was once the 100-year storm surge that took out the levee system in the whole Bay Delta area, with 1 foot rise in sea level, could suddenly become a 10-year event. And to show this in a little bit more pointed way, you can see here in different color schemes where our bay might grow to in the future. So this gets to the question of, without earthquakes or anything else, what's going to happen? Now, I'll just talk about a couple other sectors briefly and get to this punchline. As part of this same study, a group from Oregon worked with us using a dynamic vegetation calculation. And you can see here is the historical distribution of vegetation types. Most importantly is this squeezing out of certain subalpine species. And as we go out into the future, it pretty much gets moved out. And to see how that really looks, in general, we see that it's decreasing quite a bit in the future, and it's being taken over by the evergreens. These mixed woodland types are decreasing as well. Grasses are intruding as well as some desert. And the desert may be, well, due to the decrease in water availability. So this study that came out in 2004 has these following points. The temperature increases much more rapidly with the fossil-intensive future. It increases pretty rapidly in the other case as well. Most importantly, the summer temperatures are much higher than we thought, much, much higher. And heat waves and extreme temperature is going to be accompanied with it, and it's going to push mortality and energy demand off the charts from what we know right now. Precipitation, we can't really say a whole lot right now. But what we can do is say that all these other sectors are going to be impacted. I didn't mention the big wine growing industry, how everything's going to be shifted. And one of the few places that are going to be good are far northern California. Yeah, so if you're going to buy now. One of the things that we pushed legislatively is that adaptation is just going to get more expensive with time. And we need to look at this now. And that these emission pathways really aren't the upper and lower limits. The future technology, we really don't know. And we also don't know what could happen with other types of things that haven't really happened yet. So there's a lot of things out there that we don't know, and we don't, can't say this is it. So what does all this tell us? What can we do with this right now? What have we learned? Well, we've done some careful activities in the state, and suddenly we got this. And this is important. In June, Big Arnold signed S305, where he actually came out and said, we're vulnerable to these impacts. He said that temperatures threaten the Sierra snowpack. He said that it threatens our air quality, human health, heat. I mean, this came right out of this work. And he goes into all this gobbledygook. It's quite good to see. Michael Hanneman and a couple others were smiling when this was done. And so this is the other part of the proclamation. And I just wanted to read these final bullets before I finish, because this is really important. California, in a sense, is part of the Kyoto. It's part of its own country in a way, because it doesn't follow the Bush mantra. By 2100, we're going to reduce the greenhouse emissions to 2000 levels, and by 2020 to the 1990 levels. By 2050, 50% below the 1990 levels. This is important. The Secretary of the Environment, the California EPA, is going to handle all this. And this is going to be coordinated with a number of these agencies, including the California Energy Commission. And this is going to be reported to the governor. And we, myself included, are rushing like crazy to finish this big report. I'm on 6 of the 12 chapters, leading one. And the first draft was completed, and we're all writing between AGU meetings. And this report is going to be presented in January and then every other year. And it's going to include impacts on the water, public health, agriculture, the coasts, how the coasts put up with how they sustain, if you will, forestry, and how to mitigate. So finally, it just signs it off. So I'm just going to end here by saying that this is what we've done to help sustain California, and I think this was an important step that took many years to get to. That's it.
we can have Matt or follow-up questions. No?
You had your hand first.
Yeah, recent researchers reported that the decrease in the effects of the Gulf Stream on Northern Europe. Is there a similar occurrence with the Japan Stream, and what would be the effects on California?
The Kuroshio current is a very cold current, and it's got a very different behavior from what's known as the conveyor belt. And I don't really think it will impact California now. It comes from the north. It's a little different mechanism.
Yeah, you made a comment about the Northern California, and your model seemed to show a significant difference in changes affecting Northern California versus, or the Northern Sierra versus Southern Sierra in terms of snowpack and heat and that sort of thing. Do you have any suppositions as to why that?
Yeah. Northern California, Sierra Nevadas are much lower elevation. That's one of the primary reasons. The other reason, in part, has to do with this sort of bipolar nature of natural modes, the El Nino Southern Oscillation, where moisture will come to the southwest much more often in a positive El Nino phase. When you're in a negative phase, it goes way north, and so it sort of splits it. And more work needs to be done to understand how that takes place and how that affects the precipitation patterns, really.
Will the reduction of greenhouse gases that we have set as our target have any effect on the microclimate or local climate of California?
The reduction?
Well, the reduction of greenhouse gases that the governor has stated is I asked that as a climate modeler, and I never, we talk about these grids of being a certain size, and I'm really interested in the downscaling of this, whether it will have.
The short answer is yes, and the long answer is more work needs to be done.
Yeah. Could you give me an example of the yes part?
On how the reduction would affect the microclimate? Yes, certainly. Photosynthesis.
Say the inversion in the Central Valley and the
yeah. We've actually done a lot of heat island analysis and attribution, as well as in fact, tomorrow at the AGU, no, Thursday at the AGU in the afternoon, Jiming Jin, who works with me, will be presenting a very good study on the change in cropping from farmland to irrigated farmland over the last 100 years. And there's a big change in sensible and latent heat. Now, just going from a natural system to a water system, you see that. Going from a system where the emissions change, you're going to see many mechanisms, I believe associated in part with the sea breeze and how certain pumping takes place into the Central Valley. Okay. In addition to the inversions and other things.
Okay, thank you.
A lot of the California infrastructure for water goes through the Delta or through Stockton area. What happened to that?
Well, I didn't do the second half of my talk, which you know about. We've done a lot of work using what's called the CalCIM model, the Calvin model, the DSM, and various flavors of water conveyance coupled to all this. Levi Brecky, as part of his PhD, did that with us with an EPA grant. And what you find is transfers are going to just be a function of all that, and how that takes place is still a big area of research. Again, there's a good talk by Levi Brecky tomorrow at the AGU. Should read it.
So yeah, when this Katrina and Rita came along, people said it is because of the water temperature.
Yep.
Now, do these models take into account the possibility that with increasing the Pacific Ocean temperatures, we may in fact have bigger and more awesome storms and things like that?
Yeah, let me take a step back. Harry Manuel from MIT came out with a paper in Nature about 3 weeks before Katrina hit. And what he showed was this beautiful correlation with this hurricane power intensity index. And it's really the integral over time of how strong the winds blow. That's all it is. It's very simple. And he correlated that with sea surface temperature, and you see this upward trend over the last 20 years. And all he says is you're just going to expect bigger and stronger ones, and perhaps now that we have Hurricane Epsilon, more. It's an unprecedented number of hurricanes. And global climate models have very detailed process temperature in the upper layers, the structure, in the vertical profile. That, I think, is your question, and takes it into account.
So that essentially then it is likely that if there is increase in the Pacific Ocean temperatures, then the storms which come our way on the west coast of the North American continent could in fact become stronger. Is that an implication? And they may carry more moisture? Or?
This gets into the question of whether or not the hydrologic cycle is accelerating. As the sea surface temperatures increase, more evaporation takes place, and more cloud processing takes place, more velocity internal to the clouds take place, and the whole thing's advected. And as that is sort of like a pump, and it's also pushing the waves up into the atmosphere and creating what are called Rossby wave activity as well as Kelvin wave. The ocean is a mechanism, as it warms, it's controlling a lot of that. It's a clear effect on it. A lot is not understood yet, but there is a relationship.
What do you think would be the most reasonable mitigation measures for the water supply sector, say in the northern Sierra, given these changing patterns?
Water use efficiency is a primary one, and perhaps retiring cotton and rice fields, which are huge water hogs. The ag industry takes up, I think, over 60 to 70% of all our fresh water right now. And if we didn't have as much water-intensive cropping, then there wouldn't be such a large amount of water going to ag, which could then be to sustain ecosystems and other things. To me, that seems to be the no-brainer. In fact, one of the commissioners, who I won't mention, said that that is the way to go, that this should not be a problem.
There's talk in Northern European ecological circles that Italy will similarly suffer a harsh future, and that they're not really taking steps to address that now, and that Europe as a whole will bear the cost of kind of that sloppiness, which we in California may also be doing. To what extent do you think that at a national level we should be addressing kind of California's slow adaptation of these measures?
To what extent we should be addressing it at the national level?
Like at a national level, they should be saying, California, you're in danger of being drought-ridden,
I wouldn't use that language. I'd be really careful about certain words. California is in danger of losing its snowpack because of its proximity to the ocean and the elevation of the mountains. So it's in some danger of losing the fresh water that it currently has. And what is evolving right now is sort of what's known as the Western States Governors Initiative to really fix these things. It's in place. And the way these kinds of things happen is, for example, the Powley bill goes forward, so California has the strictest emissions reduction in the world at present. And so New York and other New England states are going to follow suit. And it's sort of, seatbelts. Everything kind of progresses that way after California, more or less.
How many tons are we responsible for gigatons? Worldwide, we're now 7 gigatons.
Oh, the U.S.?
So no, California. If we're going to make these goals, how many gigatons are?
I don't have those numbers on my head.
A lot.
It's been a long day. I'm sorry.
So do you have any hypotheses at this stage about the potential impacts of the temperature and precipitation changes you mentioned on groundwater? either direct or is people using
I do.
groundwater?
I guess I would say that there's an interesting thing. As you start depleting groundwater, and this has been shown in China, one of the areas that I've been working, once you start lowering it, it doubles, it drops really fast. And as that happens, you get into what's called a deficit mode. Pumping costs go way up, they skyrocket, and that's what we're positioning ourselves for. So it's an economic question. How much are you going to pay? That's what I think is going to happen.
Do you have any suggestions about ways to slow down the buildup of greenhouse gases? For example, would massive tree planting be helpful? Sequestration is a real short-term kind of thing. Certain vegetation types are going to saturate out, as far as I understand it. It doesn't go on and on and on infinitely. Geologic sequestration, I think, is more viable. You're basically putting back something almost in a fashion similar to where it came. But that doesn't slow it down. It just stores it. I don't, unless you have a big vacuum cleaner, I don't really.
You got to bury it, right, or split it on the ocean.
Well, I mean, the question is, how do you reduce the concentration in the atmosphere? And sequestration, as I understand, at least the geologic part, it's really not pumping from the atmosphere. It's associated with power plants and emitters. So it's reducing the amount being put in, as opposed to trying to, in addition, pull out.
California is committed, the governor is committed California to reductions in greenhouse gas emissions. To what extent is California also considering policy alternatives that would address the effects of climate change? For example, I'm not sure if it was tongue-in-cheek where you pointed out that San Francisco Bay will extend inland. There are a large number of houses being constructed on areas that are today prone to flooding, and those decisions are made on a local basis and without regard to the overall effect.
That's a good question, and I think I know where you're going with it. And it really comes down to people that make money from money in real estate kind of enterprise, and whether or not they can be convinced to go with certain commissions' views of things. For example, on the Napa River, they changed the watershed to an undeveloped region so that it can flood naturally. On the Russian River, it typically floods every 3 years or so, and we've done a lot of work on that. And what they've done now is we'll insure you once, and you've got to put your house up. If it happens again, we're not going to insure you. So those kind of things change behavior over time. But it's kind of like the 40 years in the desert. They've got to lose everything a few times before they make change.
If I may, I'd like to push you a little further on that. I mean, when you talk, for example, about the impacts of the snowpack in the northern Sierra, that's 60% of the fresh water used by residential customers in the state. And so there are going to be tremendous impacts. And I would like to know, on the one hand, what degree of confidence you have in the modeling and the results and the projections. And on the other hand, what you as scientists have been doing to push Arnold and policy staffers to really start to take account of those results.
Well, the Department of Water Resources has a state water plan that now has climate change in it, and we're part of it. And in it, they're working to create ways to act on all this. I mean, it's really bubbled up big time now.
A huge amount of stuff is coming out. Wait until next month when these reports, which will be released for the public in about 2 weeks, the draft. You'll see that the chapters from the Department of Water Resources state all this clearly. So that's really the short answer.
This gets back to a lot of the models that you referred to, but in your opinion, can California's water infrastructure sustain future climate change?
Yes. I believe technological advances can move us anywhere, provided that a number of things are in place. And it's not clear exactly what those things need to be just yet. Especially the levee system, the aging levee system, and the system's sensitivity to earthquakes. There's a whole slew of things that could break it. And it comes down to really the budget and those big kind of things. So, you know, you can do a lot of things if you have money. I'm sorry.
Somewhere I have heard that the West Greenland settlement, the Vikings, succumbed in about 1300 because within about a century the climate changed dramatically. First, is that true? And second, if so, what caused it? Is there any understanding what caused it?
Well, you're probably talking about the Little Ice Age.
I don't know. I just heard climate change within about a 1 century period, much earlier than man had any effect on it. Do we understand why that happened?
Again, there's a lot of natural modes of variability. There's also the beginnings of an understanding of solar luminosity and how that changes the net radiation that can change cooling and heating at the surface. So there are many layers of half answers that people will tell you, and that's as far as I want to go.
So these are the same order of magnitude as the greenhouse emissions, or much smaller? Or?
The greenhouse gas emissions have caused a warming that is unprecedented since the last ice age and beyond. And the rate at which it's warming is even much more rapid than has ever been seen. You know, that's the whole point. I'm not sure about you know, the paleoclimate because that's not really my area. I can't really comment.
So I've heard that farmers around the world got together and held conferences and talked about how they can no longer predict things that they have been able to.
Farmers?
Yeah, for people who have worked the same land for generations, and that they can no longer predict things because things are just humanity changing. And I was wondering if you think that just unpredictability is going to be a characteristic of the upcoming future, or if there are going to be things like the scenarios that showed us.
Now, would you repeat the question?
I think what she's talking about is in a person's lifespan. They experience changes in their awareness of the climate, and they can't plant at the same time as they used to because it's not as predictable as they thought. Yeah, I mean, you can talk to the Eskimos and other groups of people who are actually losing their entire life, their livelihoods, because things are changing. So that's all I can say. There's evidence.
Just to revisit your comment about the levees, I was wondering about your opinion about, you say that you worry about, the old failing levee system. There are many ecologists who advocate, flooding the Delta region and getting rid of them completely. Do you think that we need to buffer them and continue on business as usual, or do you have any?
I don't know enough about that specific, and I don't know enough about Hetch either.
You said that with improving technology, we can manage things. However, what it seems to have done from a purely civil engineering point of view, we take on the levee system and so forth, we have seemed to have gone so much against the grain of nature and how nature directs its energy. It is true that we can build for any particular area, we can build as strong a dam or a levee or whatever we want. However, in a larger sense, we'll go bankrupt, I think, if we continue to go against zoning and so forth. And we have a national insurance thing which continuously encourage people to build a building right on Malibu Beach or someplace and then give them low cost. I think technology, I understand that human mind is very creative, but I think that maybe have to be a paradigm shift that we cannot mobilize technology against the grain of nature.
You make a very good point, and I'm on this urban flood management science board for Holland. And about 4 years ago, they made the paradigm shift. They went from fighting water to accepting water. They went from always pushing it back to bringing it in. They changed their building code where the big giant tulip greenhouses have to rise and sink with the water now. There's a whole thing going on, and you should read about it because it blew my mind when I was asked to be part of that. They're doing this huge change, and the potters that are 10 feet below sea level, people that live there now are have to address this in a different way than they used to. So that's changed. Of course, Amsterdam is more, as it stands now, they think it could be 20 miles out in the sea. That remains to be seen. 1/3 of their country is below sea level.
About a few days ago on the TV, there was a geologist or somebody from, I believe it was LSU, who had done somewhat along this line. I forget the name of the person. He said that the projections were that towards the end of this century, there will be so much of encroachment because of natural sea level rise or whatever, that water will be coming so far inland. He was seriously raising a question whether New Orleans should be rebuilt. And this raises a much more profound question that there might have to be a large-scale remobilization and redistribution of populations. If we accept to go with the water, that may be one of the implications, rather than saying that technology will keep it back all the time. If we take that paradigm shift, we may have to redistribute populations.
Yeah, and for about 20 years now, 25 years now, they've been talking at very high levels about water wars, the movement of civilizations as a function of water. And of course, civilization came to be because of the water network, if you look at all the old cities. So, without getting too philosophical, we may see a long-term cycle of how society evolves with climate change, natural and anthropogenic. It's still, for your great-grandchildren to tell you. So, I don't know.
Any more questions?
Well, since we didn't hear the second part of your lecture about water infrastructure, I was wondering, in your lecture, if there are any proposals or recommendations as far as what types of changes in our water storage or water conveyance and treatment systems that would have to occur as a result of these changes.
My answer is that there's a group of people, the Department of Water Resources, people here, myself and a number of others that are maybe will have an answer in the future, but not right now.
Your maps of vegetation change. I wondered if you had that reference. I copied down Lenahan 2000.
Yeah, Ron Nielsen from Oregon State has that.
Do you remember where that was published or where I can track?
Yeah, actually, you can go to the Proceedings of the National Academy and just type HAYHO, Hayhao. That's the lead author on that paper. And then there's a supplemental materials on the web, and you can get all of it from there.
Terrific. Thank you very much.
Yep.
It seems like you've had some movement on the political side of things with the work that you've been doing. I'm wondering if you've had any inquiries or what you might be seeing going on in the corporate world, what businesses are doing in response to your work.
Yeah, actually, the insurance industry, from 1999 to 2003, I ran this NASA Water Resources Center. And Arkwright industry, insurance industry, was very interested because they wanted to not spend so much money paying people out for floods. And they wanted us to work with them to help recalculate the probabilities. So yeah, that would be the one industry that has a great interest, the reinsurance and the insurance industries.
And interested in doing what?
They are interested in paying for a postdoc to work with me and do some calculations, and I can just feed them some probability maps that they can use when they come to insuring people.
Well, you know, FEMA a few years ago said that they wouldn't insure cities and other entities that did not avoid catastrophe. That's not what they're talking about. Is it with these insurance companies that you were dealing with? They're not trying to avoid catastrophe. They're just trying to figure out how to manage.
Manage would be the right word. Another example. I do a lot of landslide theory with Bill Dietrich here, and one of his students is a professor up at the University of Washington. He generated these landslide probability maps at fine resolution, and he got in a lot of trouble because he brought it down to the house level. The USGS won't do that, you know. There's a reason for that. It gets
a very bad reason.
Yeah.
What about the defense industry and the bomb testings and the bombs and nuclear stuff and all that? Do you have anything to say?
Yeah, I'll say one thing. When I came to Berkeley lab, I heard about the Yucca Mountain stuff. And they said, 2 millimeters per year net infiltration is...
Less than that?
Yeah, less than that. And you know, we're going to go out, and they're talking about 10,000 years, 100,000 years, understanding the radioactive plume beneath the storage zone. And I have a hard time with that number, and I have a hard time with these time frames. And I've always asked them, why don't you just turn the whole question on its head and ask, how can we break today's climate to create a scenario that will be greater than their threshold? There's a lot of theoretical ways to do this, and that's as far as it went. And that was my, my contribution.
Any more questions? We have plenty of time.
Well, back to that insurance question. I mean, there's a Swiss, I don't know if it's Credit Suisse, but it's some Swiss, someone Swiss who insured. And they don't reinsure anybody who doesn't take steps to mitigate climate change in their operations. And they require a sustainability study to be done. And it might not be Credit Suisse. But that seems like it'd be a hell of a lot more useful than, you know, than brokers hiring consultants to figure out who they should charge higher rates to because they may be flooded.
I try to stay away from all that, so I can't really go there.
There's one more.
Okay, an easier climate question. So your maps didn't show the resolution right to the coast. I was wondering, so for San Francisco and other communities right along the coast, are we to expect to be part of the general warming trend, or are we going to expect colder, foggier, longer summers
That's a good question. And, you know, we're doing work right now as you speak on trying to understand future fog patterns. And it's driven by a temperature differential. And my stuff so far and other people's stuff so far pretty much shows it's going to warm somewhat. I did a thing on this heat extreme business for San Francisco, and it gets warm more often. The question of cloudiness really is complicated, and it's coupled to how the Central Valley temperatures change and how the surface water temperatures change in sync with one another and out of sync with one another. And you know, that's really what it comes down to, how that gradient changes in time. And there'll be more papers out on that.
What is the relative ratio of the snowpack storage to all the storage in all the dams in California?
Depends on the time of year. I think in April, right at the peak of snow storage, it's greater than reservoir storage. That's a general answer because I'm pretty sure that's true, that number. It's greater.
Does this imply that if you just built approximately the same number of dams as we now have, we would get enough storage to be where we are?
That's not necessarily going to be the right solution because there's a lot of more complicated types of things that percolate through the system that will have other effects, the ecosystems and so forth. You have to think beyond water when you start doing things like that. Three Gorges Dam is one of the more interesting things I've worked on as a model. And there's some real problems that we're confronted with now. The local climate is one of them, as well as sedimentation, not counting the relocation of many people. And it's still going to flood, the dam, because of all the trees that were cut down way far west up the Yangtze. So that's not necessarily the right solution yet.
But it would provide the same amount of storage.
You know, you can talk theoretically about volume stored, and yes, that may work. I don't really know if that's the best way to go about it.
You spoke briefly about agriculture in California, about the majority of the water that it uses in the state. I was wondering if there's any talk that the people are just in certain circles about actually improving the efficiency of the use of agriculture, the use of water in terms of things like drip irrigation, or improving the soil quality so it retains the water and doesn't erode soil and runoff, things like that.
I don't know much about that specific, but I do know that if you shift from certain types of sprinkling systems to drip, you'll get root rot. And you know, the main solution, I believe, is retire some of these cotton and rice fields. But I don't know too much more beyond that.
One last question.
Well, you said something about trees earlier. I didn't understand it, but my granddaughter, who's 8, eats rainforest cereal because she wants to save the rainforests. Is there any point to her doing that?
I guess it helps her idealism.
Do you need to save the rainforests? I mean,
sorry?
Will the rainforests help us in any of this, or doesn't it matter?
Well, you know, the Brazilian rainforest is being depleted pretty quickly. Sorry?
In the California rainforest.
Yeah, in the north.
Right here.
Oh. Sit behind my computer. I don't have a real answer for that.
Well, could you think about it, and I'll ask you next time I see you.
Well, I want to finish up with a comment. The spirit of this California Water Colloquium series has been to break down these barriers between science and the humanities and the social sciences and so forth, and begin to look at water in a much more broader way, because they're all so much interconnected. And today's talk has been really marvelous, because the numbers and the graphs that you presented are based on very, very sophisticated mathematical models, really state of the art. But still the final outcome was, the whole idea of all the calculation was to bring an outcome which all of us can share, regardless of whether we do science or engineering or social sciences or law or policy. And that came about, and we went beyond the science part of it. And we looked at many other issues which affect society and policy as a whole. That was the whole idea of the series, and it has been a wonderful presentation. Thank you.